translate better like that.
Okay, so it's time to start our session today. The first talk is by Constantine Caramanis about high-dimensional robust sparse regression.
Thanks very much, and thanks to the organizers for organizing and also for inviting me. So this is a talk and a theme of something that I've been interested in for quite a long time, and I'll give you a little bit of the history of what's been done and what are some recent breakthroughs, and also why this is an interesting problem. This is joint work with 3 PhD students at UT, Liu Liu, Yanyao Shen, and Tianyang Li. So to start with just a brief overview here, what is the general problem I'm interested in? Because the word robust is used in a number of different settings, but so I'm given the problem I'm interested in is I get data, and what I mean by this is that almost all of the data, but a constant fraction, come from some model P, which I care about, and then an epsilon fraction, which is an order 1 fraction, comes from some arbitrary distribution that an adversary can select. The adversary can select it even after seeing potentially the realization of the data. So and the adversary has no computational or otherwise restrictions. The adversary can also know whatever algorithm you're going to use. And the goal is to estimate some parameters of this original distribution. So this is the basic problem. Now as I'll mention, robust statistics has a long history. Now I guess the fancier word, the neural networks word for this is data poisoning. So we always have to keep coming up with new terms to keep things fresh and exciting. So the key idea that you should have in mind is you want to find the mean of a bunch of numbers, but there's been some outliers added. Okay, so I'm going to come back to this example because even though it's very simple and we all know what we should do here, it's illustrative and provides. If we look at it in the right way, it can provide the key of what we should do in a high-dimensional setting. Whoops. I guess we just restart in this case, right? Let's see. Let's see if that worked. Seems like it did. Yeah. So this has been a classical problem in statistics that has a very long history, even to the first part of the 20th century. But the focus here was not on things that respect that most of the results in the traditional literature have been asymptotic in nature and not really focused on problems that demand very careful attention to computational complexity. And in fact, there's been very little progress until recently, even for really basic problems. So when I mean basic problems, I mean things like mean estimation in high dimensions, or regression, estimating, say, top singular vector of the data.
So here, if you remove the ability of the adversary to look first at the realizations before poisoning them or whatever, that's agnostic learning, or?
Let's see. So if the adversary has to commit to Q and then you get to draw IID samples, I think that would also be challenging. I'm not sure how that would make my results better in this particular case. So the adversary can even do that. In fact, some of the results that I'll mention look at an even stronger model where the data are drawn, the adversary gets to delete some of them. So even the authentic samples are no longer IID according to the distribution. But that's not the model that I will look at. So just to give, for those that don't know about this area, until pretty recently, even the problem of estimating, say, the top singular vector of the top principal component of data in this regime where the number of samples scales approximately like the dimension, which is the regime that we would care about if we have a simple, say, Gaussian covariance estimation problem. Think about like the spiked covariance model. This is really the regime of interest. We don't want to have samples way more than that. the situation until a few years ago was stark in the sense that there was no, as far as I know, polynomial time algorithm that even could guarantee a positive breakdown point. So in robust statistics, this concept of a breakdown point is not even trying to give a specific guarantee. It's just saying an algorithm's the breakdown point is the epsilon, where beyond that, an algorithm can't guarantee basically anything better than guessing. So it means that the algorithm has no guarantees whatsoever. So basically, this is not good. So it's a challenging, been a challenging problem. Yes.
So I mean, you don't need d log d or something. I mean, even for log concave densities, you may have to go more than d, right? Is that?
Yeah. Well, okay. So in this case, I'm thinking of the easy problem where let's say I want to do. Where I want to estimate, say, the spike in a spike covariance model.
You want to estimate I see.
And then
one eigenvalue.
Yes, so it's that kind of problem. But yeah, d log d. I just mean I don't have n so much bigger than d that I could apply a one-dimensional estimator, say, to each component, and then to be able to convert, say, an infinity norm bound into on each of the individual entries into something like an operator norm. Something like that. Okay, so there's been progress since here, but I'm just setting the stage here, and let me give you an idea of like why high dimensions is really, or this dimensional regime is what's important to look at. So the classical picture that we think about, maybe if you haven't thought about robust PCA, you think, okay, I've got this cloud of points. What could the adversary do with just a few points to really mess me up? And you see that this is really the only thing the adversary can do in this low dimensional setting. Low dimensional because I have many more points than dimensions. So the adversary would be forced to do that, and so if we think about the approach that you would take here is just to pre-process your data. You can realize that these points are farther away. You could compute some Mahalanobis distance, or there's a whole host of things that you can do, and these are in the classical textbooks on robust PCA from 30, 40 years ago. But okay, this is my best attempt to draw in high dimensions. But if you're sampling from a high dimensional Gaussian, and your samples are approximately the same as the number of dimensions, you basically every single point is on its own, essentially perpendicular to every other point, and also perpendicular to the direction that you wish to recover. So it's very easy. The adversary doesn't have to do something like this. It doesn't really have to reveal itself. The adversary can just put some points. They don't even have to be that far away. They don't have to be higher in magnitude. So this is why it's harder. The problem is harder and interesting in high dimensions. There's no real pre-processing that you can do. The only thing that actually reveals the presence of an adversary is if you know the solution already, because the solution would fit the majority of your points, but not fit the outliers. So it's a chicken and egg problem in this way. So this is why a lot of interesting things. So I as I mentioned, I've been been at it for a while, and so almost 10 years ago now, we with my colleague Quan Xu and Shai Manor, we worked on this problem and found an algorithm that I'll tell you a little bit later that basically has a breakdown point of 50%, which you can see is the best possible if you're committed to outputting only a single solution. If your adversary controls more than 50% of your data, there's really nothing that you can do. So this algorithm guarantees that you'll recover something that's better than guessing, even if you have 51% of the data are not corrupted. So this is some early work on the covariance estimation problem. There was a lot of work on robust regression starting around the same time, where there was only allowed corruptions in the output. So I have my covariance, and this is what's called the dependent variable. So if you're only allowed to corrupt the labels, there was a lot of work that used essentially technology from sparse recovery and treated the corruptions, the constant fraction of corruptions, essentially like a sparse variable to be detected, and using ideas from from sparse recovery, things like algorithms like lasso, essentially, and then concepts like RIP, restricted eigenvalue conditions, and so on. We're able to show that that you can deal with this quite well. But in the setting where you have corruptions in x and y, things seem to be much more difficult. In fact, in this paper we showed that no convex method, or in any case, that convex methods are fundamentally unable to deal with corruptions in x and y, though they are able to deal with corruptions in y. That's what these works here use, essentially a convex formulation, and are able to be resilient to a constant fraction of corruptions in y. But that's that whole host of approaches where you have a convex loss function and maybe a convex regularizer. No combination of those is able to work for a fundamental reason. But we weren't able to do much better than them. Here we were only able to show that through different algorithms, not based on convex optimization, we could be resilient to a sublinear fraction of corruptions in x and y. So I can't say that we're resilient to, say, 2% corruptions or 1% of the data being corrupted. That was the best that we could do at that point. And then, of course, there have been a lot of other works that deal with different forms of corruption that are pretty different from this talk. So I want to at least mention that there's an entire line of work that deals with, for example, sparse corruptions to a low-rank matrix, trying to recover those two components. So that's what these two works are now about 10 years old, and then there's been a huge follow-up. But this is very different from this talk, so I'm not going to go into that.
Just to understand, is there a baseline according to which any algorithm would be resilient to a very small fraction? I don't know, 1 over the number of samples or something?
Yeah, so good point. So you're asking perhaps maybe the problem is unidentifiable, for example. But is that?
I just wanted to know if I take an out-of-the-shelf, non-robust.
Oh no. Yeah, no. So if you run PCA or you run just ordinarily squares and you just have even a vanishing fraction, like an order 1 number of just a constant number of outliers, you can have it can be arbitrarily bad. And this, by the way, is also true because of this high-dimensional setting. So this picture, if you just take one point and align it with one of arbitrary points, there's so much energy in having 2 points that are aligned when every other point is close to perpendicular to every other point, that even just that would, if you ran PCA, would basically pick out whatever direction that you wanted. Okay, so more recent history here has made significant progress, especially significant progress on what we had been able to do here, where we were able to guarantee that you have a breakdown point that's almost 50%, but we didn't really have strong guarantees on how well you could do. We have some guarantees on how well you could do, but these have been significantly improved, and what I'll talk about today really leverages that progress. That was really what kind of unlocked a lot of possibilities. So, and you can see that this happened very recently, just a few years ago. There was work on robust mean estimation, and even more recently, this has been followed up. I haven't seen Arti, but maybe I think she's one of the organizers of this session. So this is her on robust sparse mean estimation. So what is this problem? Robust mean estimation, you get a bunch of data in d dimensions, and you don't know nothing about the mean. There's no structure about the mean, so you're willing to get samples proportional to d. But robust sparse mean estimation is what it sounds like. You have data in d dimensions, but most of the entries of the mean are 0. So you would like to have sublinear sample complexity. And there's been lots of work on this. So Hopkins, who actually is a Miller postdoc here, in September posted some recent work on the low dimensional setting. On Monday, These authors posted something. On Tuesday, Hopkins posted an update. I was hoping to give a talk later today, just in case I'd be able to report more progress. So this is an active area, and lots of things have been happening. And importantly, this has been some enabling, in my view, for some more general approaches to robust statistics and also robust regression, which is what I'm going to talk about. The most related paper, probably to what I'm going to talk about, is work that happened also in this year on using some of these techniques for robust regression, but not in the sparse setting. So I should also mention there's another line of work that I'm not going to talk about because the techniques are not related to what we're going to use, that use the sum of squares technology to build algorithms that are resilient to outliers. Okay, so let me tell you again specifically what the model is that I'm thinking about. So I'm thinking about the standard sparse regression model, where the number of samples I have is much less than the number of dimensions, and I would like the number of samples to scale ideally like sparsity log d. We're going to need, for reasons that I'll explain, sparsity squared log d. But that would be our goal, to really have something that scales sparsity log d, because we know that in the uncorrupted model, by now it's very well studied, that as long as your sensing matrix satisfies some properties, that convex algorithms like lasso or a number of different approaches can succeed in recovering beta. So this is well known, and this is what we aspire to. So I guess this is your question. You know, single corrupted sample can really make your life bad if you ignore it and just run the standard algorithm.
Can you go back to the previous slide? That's like your model of data. It's like
this is the model for my good data.
yeah.
So the authentic points. This is my p. I had a p and a q, and this is my 1 minus epsilon fraction of the points come from this model.
And what is the matrix X? So each data.
Good question. Yeah. So my model, my matrix X in this work is going to be drawn from a Gaussian, standard Gaussian. So basically best case scenario.
Drawn from a Gaussian, but the data is actually what you said is like multiplied by a sparse vector.
That's right. So X by itself has a distribution of a standard Gaussian, and then the distribution of Y is going to come from this multiplication by a sparse vector plus additive noise that's independent.
That's only for the label.
That's right. Yeah, this is a standard regression model, and P is what I care about, and then Q is something just arbitrary, and epsilon is what I will want to be a constant fraction of my outlier. So it can be small, but I don't want it to be vanishing. Okay, so this is actually now the model that I have. So the top part of the matrix comes from my model P, and then the bottom part is completely arbitrary. And it's not just these labels that are flipped. So just flipping labels, as I mentioned, we can address using other techniques. Basically, variations on lasso will do a really good job. But those fail, and as I mentioned, there's fundamental reasons that they fail. It's not due to not clever enough tuning or something like that. Where if X is also corrupted, then we need to think about something different. Okay, so back again showing related work. So these are some of the works that I mentioned that could deal with corruptions only in Y. The much more recent work is able to deal with when I say low dimensional, again, I just mean that I'm allowed to have samples that are proportional to the number of dimensions that I have. When I say high dimensional, I mean that I have sparsity, and because of sparsity, I'm going to insist on having my samples scale sublinearly, logarithmically in the ambient dimension. And we had made an attempt some time ago, but we were really only able to get sublinear fraction of resilience to sublinear fraction of corruptions. Okay, so this is the brief summary of work on robust regression so far. So the low-dimensional setting, we basically know what to do there. And in the high-dimensional setting, we don't. We sort of have an idea, have sublinear scaling, which is really much, much weaker than what is possible in the low-dimensional setting. I mentioned the sum of squares technology. The sum of squares technology fits into this line here. I don't see a fundamental reason why that wouldn't work for the sparsity as well, but I think that hasn't. Yeah, so I don't know that. I'm not saying that can't be done, but it hasn't been done, and I don't know how to. Haven't thought about that. So we really don't know. We have essentially until now we have what I would say is a pretty weak compared to low-dimensional regression result about sparse regression with outliers when the variables are when x is corrupted as well. Now on the other hand, the kind of key results that we're going to use come from robust mean estimation and robust sparse mean estimation, and I'll explain how these work, because this is really what is the enabling technology for what I'll show you, and also the previous work on the low dimensional setting. Okay, so again, I guess this is a summary again of that, of what we know. Okay, so our idea is, since we know how to do robust sparse mean estimation, then let's think about an algorithm that an iterative algorithm that can leverage robust sparse mean estimation. This is the main tool. So if you think about any problem in empirical risk minimization problem, and think about gradient descent, at every step, what you're doing is your gradient is a sum of gradients, each one coming from a different data point. So if 10% of those are corrupted, then at every step of gradient descent, I'm trying to find the average of data, 10% of which are corrupted. So this is the key thought, that okay, so now we've learned that thanks to those other papers that I mentioned, how to do a robust mean estimation. Let me just apply that and do gradient descent. Okay, so this was the idea in the 2018 paper that I mentioned that does the low dimensional setting. Basically, they apply robust mean estimation in the setting where to the gradient at each step. But now I can't afford to do that, because even though we know algorithms like if I did gradient descent on lasso under the nice assumptions that I have, such as my authentic data coming from a Gaussian, I know that would converge without outliers. That would converge to the true solution, but the path doesn't always stay on the set of sparse vectors. The path would go through potentially dense vectors. So if I'm hoping to do robust gradient estimation at every time, I am estimating something that's not, the gradients are not going to be sparse if I'm doing gradient descent. So this program would work, but I would have to use general robust mean estimation, which means that I would need way more samples than I'm willing to use. So if I want to use sparse mean estimation, we need to use some approach that maintains sparsity at every level, and the natural thought is to basically apply a thresholding operator at every time, a hard thresholding operator, to make sure that I maintain sparsity along the entire trajectory. And this accomplishes that.
Well, why do you want sparsity? Is it for an algorithmic reason, or?
The reason I want sparsity is that the main tool that I'm going to use is at every level, at every point when I want to find my new direction, I need to find the gradient. I need to use I need that up, and that gradient is going to be an average of the gradients at every single point. Some of those are corrupted, so I want to kind of come up with a robust estimate of that. But I want what I'm estimating to be sparse, so that I don't have to use samples proportional to dimension. I want to use fewer samples, so I need that thing to be sparse. Okay, so basically this is a simple idea, and what you need to show here is two things. You need to show that you can do robust sparse mean estimation on the gradients. And you need to show also then that that iterative hard thresholding is stable. Okay, so these are separate in the sense that if you can show that iterative hard thresholding is stable, meaning that if there is some error at every stage, then you can control your error of the output. Then basically you can, anybody who comes up with a robust sparse mean estimate that works on the gradients, you can plug those in. So those are separate parts. Okay, so what we do is basically follow out this agenda. So we show that that IHT is stable. So this means that if you have a robust sparse gradient estimate, I had to use some acronym here. So if you have a robust sparse gradient estimate that promises a particular error, then our result tells you that if you just plug that directly into IHT, what kind of error will this suffer at the end of the day? So I'll describe two different procedures. One is an ellipsoid-based algorithm that's used as a robust sparse gradient estimate, and explain a little bit how that works. That basically requires quite a bit of computation. So then I'll improve that basically by an order of the dimension, so an order-wise faster, using a different robust sparse mean estimation algorithm. So basically there's two parts to these results. The first is giving a faster, by a factor of d, which is the dimension, robust sparse mean estimation algorithm. And then also showing that any robust sparse gradient estimation algorithm, if you plug it into IHT, it would give you, if you tell me what your guarantees are on your RSGE, then I'll tell you what error you're going to have for iterative hard thresholding. Okay, so it's interesting to think about what goes into these ideas of robust mean and covariance estimation, and it's helpful to think about the really simple problem of the mean versus the trimmed mean, the median, and ask why that works. And basically, one way to think about this is that if I have a Gaussian and I want to estimate its mean, this is just in one dimension, and you throw in a bunch of you throw in some points to confuse me. If I say 10% of the points, if I tell you that I'm going to throw away 10% of the points, and it will be the biggest 10% of the points, what are you going to do? Well, you basically can either put huge points to try to screw me up, but they're going to be thrown away by the trimmed mean, so that's not a very good idea. Or you're going to basically be forced to put the points in very close to the true mean, which might somewhat confuse me, but won't confuse me very much. And the high-level idea here is that what we're doing with trimmed mean, again, just means that you throw away the 10% largest points. So the reason that trimmed mean works is that for a distribution like the Gaussian, if I remove the points that contribute most to my estimator, in this case the mean, it doesn't actually affect the mean very much. So when you throw away the biggest points, those are the points that are contributing most to your calculation of the mean. It's not the small points that contribute most, but because of the way the Gaussian is, most of this doesn't actually affect your calculation of the mean. On the other hand, if you're only allowed to add 10% of the points, you're the conniving adversary, and you put the points very far away, trimmed mean is awful for you. So this is the.
Are these spherical Gaussians?
Yes. Yes.
Because if it's not necessarily true, they are not spherical, right? I mean,
that's right. But for this result, you don't need it to be. Actually, you can do slightly better if it's spherical, but if it's controlled.
Controlled maximize.
Then you can follow the same story. So basically, how this concept of how we remove points that contribute most and then use only the remaining points is another key thread that links all of these papers together. They're done in slightly different ways, but this is the key one of the key ideas that makes mean estimation and covariance estimation possible, even when you have outliers. It's this simple idea that works for trimmed mean. So more concretely here, the idea is that you remove some fraction of the data, and remove could be actually remove or some soft version where you just downweight, so that the first and second moments satisfy a certain property. And I'll tell you some examples of this so you can get a flavor of how essentially all of these results, where they come from. Okay, so back to the mean. What is this property that is satisfied? So you have 100 points, and you know that 10 of them are corrupted. So if you remove 10 and you find out that the remaining 90, the remaining subset, has a similar mean and trimmed mean, this is a really good indication for you that you removed the bad points. And so in other words, if 90 points come from a Gaussian, if I have 100 points, 90 of them come from a Gaussian, and I find those, and I look at those 90 points, and I compare the mean of the 90 points and the mean of the 80 points after I throw away the 10% biggest, those two numbers are pretty close. And that is a property that it basically certifies that the points that you have don't have really, really bad outliers. And it's this idea of basically checking to see if your remaining points, the ones that you didn't remove or the ones that you didn't downweight, satisfy a certain property. This idea is used in different versions. So for example, in our older work on covariance estimation, the property that we used was very similar to this concept from the mean. Basically, you say that if I have a candidate principal component and I project all my data onto there, if the variance of those points is close to the variance if I trim 10% of them, I'm using 10% as my stand-in for epsilon, then you know that you found a really good, you know that you found a good direction. So other work uses some similar, again, the concept is similar. So in these two works, they don't throw away points, they use a soft, so they downweight points. And the property that they have is that a particular second moment has small enough operator norm. And you know that it has to have small operator norm because of some assumptions of the problem. This is like these require the side information. So basically, the deviation of the second moment from some side information is small enough. That's a property that certifies, similarly to this property, that's a property that certifies that your remaining samples or downweighted samples that you have are that you've successfully downweighted or removed outliers.
So this property of things remaining the same when you remove the trimmed part, and then when you remove the extremes, relies heavily on symmetry of the distribution, right?
It definitely relies on properties of the distribution. Yeah, that you have to know. Yeah, that's correct. Yeah. Okay, so get a few more details here. So basically, the way that these are the results that we use. The way that these work is that they show that if you have a deviation in the mean, because the mean is what we want to estimate, this implies that you have a deviation in a particular calculation of a second moment. And what these results do is they say, okay, I'm going to basically, if I detect that I have a large deviation in the second moment, then they use an ellipsoid algorithm over the set of weights to find a way to improve the weights and downweight points away from the outliers. So this requires using ellipsoid algorithm, which forces you to do a lot of iterations, and this is one way where we can improve this setting. So how much time do I have?
8 minutes.
8 minutes? Okay. Okay. So where does the sparsity play in here, and also where do our distributional assumptions play in? They play in a pretty important way. So. So this is what iterative hard thresholding does. It computes the gradient and then it thresholds it. PK just keeps the top k components. So if you compute what the gradient is, because of our distributional assumptions, the expected gradient over just authentic data, not over my corrupted data, is exactly going to be my current iterate minus the optimal solution. And this is something that's sparse. Because I'm always thresholding, and because my assumption is that I'm trying to recover something that's sparse, then the difference of these also is going to be sparse. In worst case, it'll be twice the number of non-zeros, but it will still be sparse. So you can see here, this kind of lays bare where the distributional assumptions play a very important role, and also why I need to make sure that all along my trajectory I'm sparse. Because if I were just using something like, say, lasso, then there is no reason that my iterate would be sparse. And so even under these distributional assumptions, there is no reason that the gradient that you're trying to compute needs to be sparse. So this is, in my opinion, is extremely limiting. That's where we are right now, and you can see that that is important because if instead of the identity here, if I have an arbitrary covariance matrix, then that will potentially destroy my sparsity. But this is something that we're working on, and this is something that's needed if you want to consider interesting problems like, let's say, basically like a graphical model estimation problem. You're going to have a covariance matrix that's not going to look like that. So this is an important thing to deal with. So
again, so you need to be sparse at the solution. You also want to maintain your sparse at each step.
At each step, that's right.
That's for computational reasons, or why do you want to be sparse at each step?
So I want to be sparse at each step. I want to be sparse in expectation over the good samples at each step. Because what that's saying is that so this is my algorithm. This is what I need to estimate. And some of these are corrupt and some of them are not. Okay? And I know that the expected value of these, the non-corrupt, the expected value of the gradients, gi is a gradient of each point. The expected value over only the distribution of authentic points has this form.
So you know if you're sparse at each step, you're okay on good guys and you insulate yourself against the bad guys.
Yeah, so if I'm sparse at each...
Yes, you might get infected by them, even if the solution at the end of the day is sparse.
So I need to know that in expectation I'm sparse, my update in expectation is sparse at each step, because that means that what I'm basically trying to estimate the sparse mean of a bunch of vectors. So that's the reason, because the key technology that I'm using is this robust sparse mean estimator. That's really important. That is critical here. Okay, so basically, let's see what I have time to tell you about the ellipsoid algorithm. I mentioned that it essentially computes deviation around a particular. So the side information that gives us the key property that I mentioned for the ellipsoid algorithm is that you should be concentrating around this matrix. And you can compute deviations, second order deviations away from that, and that basically certifies whether or not your mean estimate is good or whether it's not, and how to improve. And okay, so there's a lot here that I'm not providing details, but I do want to say that the key idea in this paper is that if in order to convert the ellipsoid algorithm to work for sparse mean estimation, then it's enough to just check second moments. Not only, I don't need to check the deviation of the second moment from this matrix, only submatrices. So I need to basically look at I need to look at how sparse, or not sparse, but all submatrices, k by k submatrices of the second moment, how those deviate. And that is exactly a sparse PCA problem. So basically if you want to compute an operator norm, but only over vectors that have k non-zeros, this is fundamentally the sparse BCA problem. And so the main idea is showing that even in this setting, convex relaxations to the sparse BCA problem are good enough to detect this deviation and to tell you how to improve your weights. So this is essentially what this says. This is the convex relaxation to sparse BCA, and the key result is telling us that if this value is small, that's like a certificate that you found that your estimate of the mean is good enough. And if it's big, it tells you it gives you a separation. It serves as a separation oracle and tells you how to downweight the weights. And you can use this technology using essentially the ellipsoid algorithm. So that is that in a nutshell. But you need dimension squared calls in order to run the ellipsoid algorithm with a generic separation oracle. So I guess So basically, instead of that, you can get rid of a factor of d, and make only d calls by, instead of working over with soft weights, you actually just discard points. So I think I'll skip the details there. Basically, the idea is just you get a score for each point, and then you just throw points away randomly according to those weights. So. And then you can show that if you do this enough, basically using kind of martingale techniques, you can show that if you have epsilon fraction of points, then if you do that many iterations, exactly how many you would expect, you have thrown away all the outliers that actually affect your estimate. Possibly some outliers remain that don't affect your estimate, but you don't care about those. Okay, so basically putting all of these things together, let's come back to the overall agenda of iterative hard thresholding plus some robust sparse gradient estimate. So what this result says, this is the meta theorem that basically says that if you have a robust sparse gradient estimate of quality whatever it is, so you're the person who came up with that, and you just give me the guarantees of your robust sparse gradient estimate, then if you run IHT using that as a subroutine at every step, then the error guarantees that you have are basically the square root of whatever guarantees you had for the square deviation of your gradient. So this is essentially saying that you don't accumulate error. If you use the ellipsoid algorithm, you can show is an epsilon squared, sigma squared. So sigma is your additive Gaussian error, and epsilon is the fraction of points that are corrupted. So basically putting this together tells you that if you use IHT plus ellipsoid, then you're guaranteed to have this many errors. So for example, what this shows is that if you have no additive error, then you get perfect recovery. So in other words, what that says is if I have linear equations, and then you come and add arbitrarily corrupted linear equations, so sigma is 0, epsilon is not 0, then if you do iterative hard thresholding with the ellipsoid algorithm, you get perfect recovery. So you can deal with sparse, you can solve linear equations with a constant fraction of corruptions and recover exactly the solution. And that, on the other hand, if your error is 0, then this is the result that you would basically expect, this kind of dependence on sigma. Okay, and then the final slide is that for the filtering algorithm is order d faster, and you pay the price that we have now a worse dependence on epsilon. The previous dependence on epsilon is the best possible that you can hope for. There are some lower bounds that have showed that. But this is still good enough to get you exact recovery for example, in the linear equation case. So, thanks very much.
Let's say there is